Okay, here we have subsets of size 3 of the first 20 positive integers. And we want to know how many of those subsets have at least one, maybe more of these elements, 1, 2, 3, 4, and 5. And it gives an example of 2 that would count and 1 that would not. So first thing, set is a collection of elements here. In a set, you don't have something showing up more than once. So we wouldn't have 1, 1, 7, for example. And also in a set, when you see these brackets here, the order does not matter. So 1 to 7 would be the same as 7 to 1. So just a couple things about sets. And I didn't take off for that kind of understanding, but I do want to make sure that you realize that. So two main ways to approach this. One, we could get the total number. So because we don't worry about repeats, we just need to choose 3 out of the 20 numbers, and that would be the total number of subsets we could make, minus the amount that don't have any of these elements. So this would be the complement of everything with at least one. So minus the ones that don't have any would just be choosing all 3 from the numbers 6 to 20. So there would be 15 possible choices there. We're taking 3 of them. And these are all the subsets that do not have 1, 2, 3, 4, 5. Subtract from the total number would give you 685. Another fine way to do this would be 3 cases. So since it says we contain at least one, let's say we contain 1 of the 5, 2 of the 5, or 3 of the 5. Those are the only 3 possible cases. They're not going to overlap. They're mutually exclusive, so we can just add them together here. And it's important that in each case to remember that we are still selecting numbers from the other 15, which is why we have 15 choose 2, 15 choose 1. 15 choose 0 does not actually add anything. This would just equal 1 on this part of the product. But if you just want to see the pattern how these are always adding up to 3 here, the number of balls we choose. Okay, number 2 here, we had 4 balls, each with an integer on it. Many of you asked me for clarification, which is a good thing to do during the test. If you're not sure, could you have repeats? And yes, indeed you could. So 0, 0, 0, 21 would be fine. 1, 1, 2, 17 would be fine. Now you could try to figure out all the ways you could add 4 numbers up to 17 and then figure out the number in each case or the probability of each case. But that would get very complicated and very easy to make mistakes. So this is very similar to the one that we had done in class with the Mona Lisa and the Picasso, or the Da Vinci, the Picasso. Also that take-home, or the exit slip I gave you one time, where we had a certain number of fixed balls and a certain number of free balls. But the basic strategy here is to divide it into 4 categories, so 1 for each of the 4 colors, and then we just place the 21 balls inside here. So essentially we have 21 balls and 3 dividers, which gives us 24 items, and we need to choose any 3 of them for the dividers and then fill in the rest with balls. Of course, 24 choose 21 would also be fine. This is also, if you remember the physical demonstration I did on my desk where I had those dividers and then we had those kind of clear slips of onion paper. This is that same case. On part B, the only difference is we know that there's going to be 3 balls, if you want, within each category. And so we really don't care about those. We know that red will be at least 3, yellow, green, blue. So that's 12 balls that are essentially fixed, which gives us only 9 of the 21 which are left free. So it's the placement of those 9 that's important. So then we have 9 balls, 3 dividers, which gives us 12 items. Choose the places for the 3 dividers, and then the 9 balls will go in the other positions. Or, of course, 12 choose 9 would be perfectly fine also. Notice that it doesn't matter the order that the colors are coming in. So some people took 4 factorial to rearrange these colors. I'm not saying it's impossible to go that route, but certainly it doesn't appear that that would be a quicker way to solve the problem. Number 3, so we just have these different dice, 2 reds, 3 blacks, and a white. And so the probability of getting red on one dice is 2, 6, 3, 6, and white 6. And these probabilities are the same for both dice since the dice are identical. Now we want the probability of getting a same, so there's going to be 3 cases. Either we get red, red, black, 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 or white, white. And in each case, these are independent, so 2, 6 times 2, 6, so on. We add to get 7/18. Okay, we have question number 4 here, different denominations. So again, I used this vocabulary word because it was exactly as it was used in the original problem in your homework. If you didn't know, I would tell you on the test, but this means ace, 2, 3, 4, 5, 6, 7, 8, 9. So there's 13 denominations there. And then, of course, 4 different suits: hearts, diamonds, spades, and clubs. So different denomination. Let's just look at a couple ways to do this. So we really want the probability that the denomination 1, 2, and 3 are all different. And that's what this notation is saying right here. Since we don't know that they're independent, and in fact they're not independent, we use the general rule of multiplication, which is we get the probability of the first times the probability of the second given the first times the probability of the third given the first 2. So the probability of getting the first to be a different denomination of anything that's been shown so far is 1, because it could be any one of the 52 cards, and we're not going to repeat a denomination yet. Now on the second one, probability of getting a different denomination on the second, there's only 48 cards left. There's 52 total cards in the deck. 1 we've already chosen. 3 will be the same denomination as that first thing we chose. So that leaves us with 48 out of the 51 remaining cards. Given those two, when we look at the probability of getting a new denomination on the third, we have 48 options because we had 52 minus basically the 4 cards in that denomination and the 4 cards in this denomination, which is 8. So that gives us 52 minus 8 is 44 out of the 50 cards remaining. So we could calculate it directly like that. Another way to look at this more combinatorically is we have 3 different denominations. We know we need 3 different denominations, but we can't stop there. If we just choose 3 of the denominations, we have, say, a 2, a 6, and a 7, but we don't know what those 2, 6, and 7 are. We haven't, remember when we're doing these playing card problems, one of the things I mentioned, we want to make sure we know exactly what the playing cards are up top here. So if I just got 2, 6, 7 and stopped at that, I wouldn't know what suit they are. So this is that 4 choose 1 to the 3rd power. I'm choosing a suit for each one of those 3 denominations. So maybe heart, spade, club in order of the 3 that I chose. And then 52 choose 3 ways to do it. That will give you the same answer. Different suits. Again, we have the same way that I did it the first time. After choosing the first one, which is guaranteed, the second one, there's only 39 because 13 of the cards are eliminated. 1 we already chose. 12 of the cards have the same suit as that first card we chose. So that leaves us with 39 out of the remaining 51 cards, and so on. Here's 2 suits gone. Another way to do it, so this way down here is similar to what we did there. We would have choose the 3 suits, 3 out of the 4 suits, and then get the denomination for each one. And it's okay if the denomination is the same, so we just keep that 13 choose 1 all 3 times over the different number of ways to choose it. Now this one's a little harder to understand because we have to account for duplicates, But let's say we chose our first card. We have 52 choices. Our second card, we can choose anything except cards that are of that suit. So that gives us 39 choices. And then 26 means we're avoiding the suits of the first two. Over 52, choose 3. So why isn't that the correct answer just as it is right there? Well, first of all, if you divide it out, you'll notice that the answer is somewhere around 2. And since we are looking for a probability, it should never be higher than 1. So that would be a tip-off right there. But another way of looking at that is that there are, if we chose, for example, the ace of spades, ace of clubs, ace of hearts, we don't have to choose the same value, I'm just using these. Then we go through again, we could choose the ace of hearts, ace of spades, ace of clubs, or the ace of clubs, ace of hearts, ace of spades. Notice that we could go through several times, in fact, 6 times exactly, no matter what 3 cards we chose, and we would just get those same 3 cards in a different order. So they're gonna, each set of 3 cards is gonna show up 6 times here, so we need to divide out by the duplicates. Again, I think this is more complicated to understand. I think these two are more straightforward. This is a possible way, but do keep in mind that there are duplicates you have to account for. Okay, so number 5 here, we have a Bayes. I had originally done this problem, but then it duplicated number 4, and I wanted to get Bayes in there somewhere, so that's why you see this crossed out. So we need the probability of an ectopic pregnancy given that you're a smoker. We need the probability of smoker given that you have an ectopic pregnancy. But part of your given information is that smokers have twice the risk of an ectopic pregnancy as non-smokers. So this is a key way to interpret that statement there. And then the 20% of the women are smokers. I think most people got that. So let's just represent here this probability of having an ectopic pregnancy given that you're a non-smoker, so that's smoker complement, so non-smoker equals X. Because once we plug it into Bayes' formula here, notice I'm giving the complete denominator for the probability of having an ectopic pregnancy, so you have whether or not you're a smoker or a non-smoker. And here we have 2 times X, right? Because if probability of ectopic given non-smoker is X, then we can just sub that in here to find out that the probability of ectopic given smoker is 2X. 0.2 probability of smoker, and then we fill these in. Simplify, get 0.4x over 1.2x. The x's cancel, giving us 1/3. So notice we really didn't even need to know what either of these probabilities were, as long as we knew that this one was twice as small as this one. In other words, this one was twice as large. Okay, finally we have another one. For part A, the key here I think is realizing that the probability of getting greater than or equal to 1 red is the total probability minus the probability of 0 reds, which would be choosing 6 out of the green and blue balls over 6 out of the total 24 balls. This is probability of getting 0 red, subtract it from 1, it's greater than or equal to 1 red. Of course, you could go through and calculate number of 1 red, 2, 3, 4, 5, 6, add them all together. That's also perfectly fine, just takes longer. For part B, 2 ways to do it. We could set up a Bayes theorem. I think the way I was trying to promote in class more was just limit ourselves to the world where no red balls are chosen. So in this sense, we don't even have any red balls. We have 8 green balls and 10 blue balls. We choose exactly 2 of those 8 green balls, leaving us with 4 out of the blue balls. That'll be a total of our 6 balls, out of the total ways that we could choose 6 from those 18. So notice all of this completely ignores the fact that there ever were red balls, which is what we want to do in this world of given that no red balls are chosen. And this would give us the total